All right. In this chapter, we are going to talk about atoms and radioactivity. And there is a typo here on your notes. This will say chapter 9. And so when we talk about radioactivity, it's important to first talk about what it is, but we also want to talk about some applications as well as some kind of pivotal scientists. So I have different images here. When we think about radioactivity, we probably think about a couple different things. So one is, right, the symbol. This is the symbol for radioactivity. But also the image of this woman probably comes to mind, and this is Marie Curie, sometimes called Madame Curie. And she was the first woman to become a professor at the University of Paris. She also discovered radium and polonium. She was the first woman to get a Nobel Prize. She was the first person to get a Nobel Prize in two different fields, chemistry and physics, and thus far has been the only person to get a Nobel Prize in two scientific fields. There have been other people who've gotten Nobel Prizes in science and the Peace Prize. And so, but her work and Becquerel's work really kind of started this chain reaction, you might say, of research into radioactivity. Other people that are really important in this are the two people shown in the bottom image here. This fellow is Otto Hahn. Right? And this woman is Lise Meitner, and some people pronounce that as Lisa, but from what I saw, I think it's Lise. And these two people worked on nuclear fission, right? And so when we look at this, right, Otto Hahn a guy named Fritz Strassmann and Lisa Meitner are really credited with nuclear fission. And so these people found kind of in mid 1938 that bombarding thorium with neutrons produced different isotopes. Now, they were in Germany, particularly when you think about Lise Meitner. She was the first woman to become a full professor in Germany, but she lost that position in the late 1930s because she was Jewish. And so they were going through this research. World War II was in full swing, and in mid to late 1938, kind of after or while these things were going on, she fled to Sweden. If you have a chance to fall down a wiki hole, reading about her life and the efforts to get her out of Germany I find really fascinating. And so she, with her nephew, which is Otto Robert Frisch, determined the physics of nuclear fission in 1938, right? Now, in 1944, Otto Hahn won the Nobel Prize for nuclear fission, and she was any other contributions were really ignored. She was nominated 19 times for the Chemistry Nobel Prize and 30 times for the Nobel Prize in Physics, and was never awarded either of those prizes. Again, I find her life to be really interesting. If you have time, that's a great wiki hole to fall down. Other places that we see radioactivity can be decorative, right? So, for example, radioactivity was used to paint the watch. Radioactive materials were used to paint the watch faces that soldiers would use in World War One and two to see what they what the time was in the trenches, because it would glow in the dark, right? It was also used in glassware. So this is Vaseline glass. And I have some of this in my office, so my hope is that I'll remember to bring it to class. But if I don't, remind me, because I have some of this and we can pass it around. And it's got uranium in it, which is why we have that yellow color, and it will glow. And then the other kind of great thing about radioactivity, besides the production of energy, is that it can be used in nuclear imaging. And we're going to talk about that, not in this screencast, but the next screencast. So I find all these images really interesting. And so I hope this gives you a little bit of history before we jump into the nitty gritty of definitions and science. But without further ado, let's jump into that kind of nitty gritty. All right, so I want to review some things. So we did this earlier in the class, and so I just really want to just dust off brain cells really quickly. So I always love images that go from big to small. And so let's start over here. We have lithium metal. Lithium's an element. And we know its atoms are arranged like this in a metal, so they arrange into a lattice. And then when we look down here, and I don't know why we have these stray marks, but we'll ignore them for a moment. When we look down here, we remember that we have in the atoms, we have a nucleus. The nucleus is composed of protons and neutrons. Protons have a +1 charge. Neutrons are neutral. And then in a cloud outside of the nucleus, we have electrons, and this is called the electron cloud, and electrons are negative. Now, I like this table because it shows you electrons, protons, and neutrons. It shows you common symbols that are used, the electrical charge, relative masses, which I really love as a review, right? Protons and neutrons relatively have about the same mass. And then electrons are about 1/2000 smaller, as well as the location. So electrons are found outside the nucleus, and protons and neutrons are found in the nucleus. I want to remind you about one of the ways that we can show information about an atom. We can put the chemical symbol here, the mass number on top, which is the number of protons plus neutrons, and then the atomic number on the bottom. That's the number that is on the periodic table, which is the number of protons or electrons if it doesn't have a charge. Now, when we talk about this, we also remember that this carbon can be written as carbon 12, where that is the mass number. And you have to look at the periodic table to find the atomic number. If you don't have a periodic table handy, my suggestion would be to pause this and go ahead and grab your periodic table because we're going to use it in just a minute. I also want to remind you about isotopes. So here are the symbols again for isotopes. The number on the top is the mass number. The number on the bottom is the atomic number. That's the symbol. And so these are isotopes of calcium, as well as the number of particles in each. And so you can see calcium 40 is here, calcium 42 is here. We can look at the nucleus of both these and see they have the same number of protons, but a different number of neutrons. So their atomic number stays the same, but their mass number is different. They don't have a charge, so both of these have the same number of electrons, which is the same number of protons. So just as a reminder, when we think about the definition of isotopes, these are any atom that have the same atomic number, but different masses. Okay, so we have the same atomic number, we have different masses, and the reason we have different masses here is because we have a different number of neutrons. Okay. I want to remind you that elements occur as a mixture of isotopes. We've already talked about this, so we're just dusting off brain cells a little bit. And so I want to show you carbon. Carbon is mostly carbon-12, right? But there is some carbon-13 and carbon-14 isotopes, as well as a few others, right? And so when we look at the atomic mass of carbon, it's 12.01. It's closer to 12 because there's a greater percentage of carbon-12 found naturally in nature, okay? Because it's a weighted average. And so you can see here, right, 90, and we've done some rounding, 99% is carbon-12, 1% is carbon-13, and then just a small amount is carbon-14. And so when we look at the atomic mass, this is the average atomic mass of all the carbon atoms. And so that's why there's a decimal that's going to be shown there. But when we look at the individual isotopes, so for example, when we look at carbon-12, this is that individual atom. And so because it's the individual atom, we can look from this and say, okay, it's got 6 protons and it's got 6 neutrons, right? And then we can look at carbon-13 and we can say, okay, it's got 6 protons but 7 neutrons. And so when we have the symbols that look like this, we are looking at the individual atoms. Now, let's get into the new stuff. Let's get into radioactivity and things that are radioactive. So when we talk about radioactivity and things that are radioactive, this is just a description given to elements who emit energy and particles. Now, this occurs in a nucleus that we call unstable. And when we talk about this, these a lot of times are called radionuclides. And radionuclides are just the term that's given to a atom that is radioactive. And it's important to understand, right, that one isotope of an element can be radioactive. And so we would call that a radionuclide, right? And others are stable. You're also going to hear the term nuclide, and this just refers to one atom. Now, I love this visual. This is a visual of radioactivity, and the specific radioactivity here is alpha decay, which we're going to look at in the next slide. But when we look at this, what we find here is we have a nucleus, and the nucleus gives off a particle, and the resulting nucleus after it gives off that particle is something different, okay? And so a lot of times too, in this instance, we have energy given off, right? Not always, but in many cases, that's what's going on. So there's 5 types of radioactive decay we are going to talk about in this screencast. We're going to talk about alpha decay, beta decay, gamma emission, and positron emission. Okay. When we talk about this, these 4 here are collectively called ionizing radiation. And all this means is they are going to produce a trail of ions through the material they penetrate. Now, when this happens, they change the chemical composition of the material. Right? And when that material is a living tissue, you can end up with radio-induced illness because of this. And so that's one of the kind of side effects. Now, I want you to look at this table. This is a really great summary table for what we're going to learn in the next few slides. And what I want to show you here and what we're going to dig into are nuclear equations. And so these are summaries of the different types. And I know gamma is not on here, and we're going to talk about why in a second. And then the change in the atomic number and the change in the mass number. Everybody learns in different ways. So I just like to give you different ways to look at the same material, really. Now, when we talk about nuclear equations, these represent the process of radioactive decay. And what happens is you have a nuclide that breaks down and it produces a new nuclide and then a smaller particle and or energy. And so we need to first talk about the different symbols that we can use for the small particles. Okay, so for alpha, we use an alpha here or 4,2 helium. Sometimes you will also see like a 4,2 alpha like that. So I wanted to give you a heads up. Okay. Then for beta particles, we see a beta, a 0, -1 e, or sometimes we can see a 0, -1 beta. Gamma particles are a 0, 0 with the Greek letter gamma, a lowercase letter. Positron are 0, 1 with an e. So these have the same mass as an electron, but the opposite charge. If you notice, the beta particle has the same mass and charge as an electron. And then we have a neutron, which is 1, 0 n. So let's talk about alpha decay first. Alpha decay occurs in many different types of nuclides, and it's going to be really present in some of your heavier nuclides. And so what happens here is this is an image of what happens. You've got uranium-238. Remember, this can also be written as uranium-238 like this. And it goes through some kind of decay event. And when it goes through decay event, basically this nucleus, right, spits out a helium or an alpha particle, 4,2 helium, where it's got 2 protons and 2 neutrons. And then it spits out a whole, and then this turns into a whole new atom, right? It's no longer uranium because we've lost 2 protons. And so now if you look at your periodic table, you go from the element 92 to the element 90, and we've got thorium here. So when we look at this, these reactions are still balanced. And so, for example, if we look at the top numbers, this is 238 here. And when you add 234 and 4, oops, that gives 238. So those top numbers need to add up to equal each other on the different sides of the arrow. The bottom numbers also need to equal each other. So for example, if we look at the bottom number here, there's 92, 90, and 2. What you're going to see is that 90 plus 2 is 92. Now, I want us to look at an example of how questions will be asked. So questions will be asked like this: 245, 96, curium. So this is curium 245. And it'll say this goes through an alpha decay. And so you'll say, okay, I know what alpha decay is. It's 4,2 helium here. And then it'll say, what's the new nuclide that's produced? And so what you have to do is you have to ask yourself, all right, if I've got 245 here and 4 here, what can I add to 4 to give me 245? And so you can say, well, I know that 241 plus 4 equals 245, right? So that's good. And then you have to ask yourself, all right, what can I add to 2 to give me 96? And when you do that, you say, okay, well, I know it's 94, right? And so then what you do is you say, okay, I know this new atom is going to be 24194. And then to find the chemical element, you need to look up the atomic number on the periodic table. And so I go to my friendly periodic table, I find 94, and I see that it's plutonium. And so that's my new nuclei that's made. So this is the process of alpha decay. The next process we're going to talk about is beta decay, which is shown. I've got the symbols here on the right side: 0, 1, 0, -1 beta, or 0, -1 E. Sometimes it's just beta. Your book uses that sometimes. And so what we're going to see here is kind of the same idea, where the two numbers here, 131 and 0, equal 131. So those top numbers are balanced. And then we have 53 here. And so 54 plus -1 is 53. This is the trickiest one because you have to remember, like, hey, when you add -1, it goes down by 1. And so just pay attention to that because sometimes we get into a pattern of doing math a certain way, and then we throw this in as a curveball. It's not that we don't know, it's just that we're in a pattern of doing things, and so just pay attention to that. So the way this question would be asked, for example, is you have carbon 16 and it goes through beta decay. So you know we've got -1 E here, and it could ask, okay, what's the new nuclei? And so we would say, all right, well, we know the top number there is going to be 16 because 16 plus 0 equals 16. And so what would I add to -1 to equal 7? So we would say, well, that would be an 8. And so we go to our periodic table, we see the element 8, and that would be oxygen. And so that's the second type of decay that we're going to see. Now I want to talk about gamma emission, and I want to build off of that previous example where we had 131 iodine. And so when we talk about 13153, there we go, 53 iodine, right? And I said, look, it's going to go through beta decay. It also releases a gamma particle, which is energy, okay? So sometimes gamma is produced with other products, okay? So we can see 2 particles here, and this is just a really high energy particle. Sometimes it'll be the only thing produced, and when it's the only thing produced, a lot of times you'll see an M here or sometimes an asterisk, right? So sometimes a little star, okay? And this just says, look, it's a meta isotope. So we've got 9943 technetium here. And what that does is when it undergoes the decay, it's going to go to 9943. So nothing changes, but the M goes away and you have a gamma there. Now, maybe the burning question in your heart is, Dr. Pierce, how would I know that when this goes through beta decay, it also gives off a gamma particle? There would be no way to know unless you were told in the problem. Okay, so I don't want you to worry about how you would know. The context clue here that you would know that this is going to go through gamma decay is if there was an M and it said, look, this is a meta isotope, that should scream, hey, look, it's going through gamma decay, or if there's an asterisk. Okay, so those are your clues. But for here, there's no clue. If there was an M, then you would know. But you would have to be told. Okay. Now, we can also have positron emission. This is where a positron is emitted from a nucleus. And you can see here again, 11 plus 0 equals 11. 5 plus 1 equals 6. I want to remind you, these have the same mass as an electron, but an opposite charge. And so an example problem of this would be if you had 11854 xenon. And it goes through positron emission. So you would say, oh yeah, look, I know it's 0 plus 1e. And you can show it two ways. You could either show it as 1 or plus 1. Either is fine. And then it would ask, what's the new nuclide? And so you would look and you would say, well, I know the top number there, the mass number is 118. And then the bottom number would have to be 53, because 53 plus 1 is 54. And that would give me iodine. Okay. Then the last type of radioactive equation that we're going to look at is electron capture. So sometimes the nucleus captures an electron from the electron cloud. And when that happens, right, you can also produce a new nuclide. And again, 37 plus -1 would give you 36. 81 plus 0 would give you 81. So you can see how these numbers, or how these equations balance. Of course, we'll do more work in class practicing this. If you have any questions, please feel free to stop by my office.